The additional fluid property that is needed to be able to explain this difference in behavior is fluid viscosity. To understand this property, we're going to consider the following ideal situation. Imagine that we have, in this idealized experiment, two flat plates which are going to be infinite on both sides. So it's an idealized situation so that we can explain what's happening. And also, this is going to be all filled with a fluid inside, between the two flat plates, okay? Infinite flat plates. Two infinite flat plates. Now the bottom plate is going to be fixed and the top plate moves sideways due to a load P. So this one in the top is going to move due to a load P, and the one in the bottom is at rest. We're going to say that the distance between the two plates is equal to B, and we're going to imagine a line here that goes from point A to point B in the two plates, and if this was a solid, then as the load P is applied sideways, then the top plate would move so that now the line AB is going to be on line AB prime and is going to move by a certain angle. Let's call this angle delta beta, and if the material between the plates is a solid, then the top plate would be displaced a certain distance and remain there, reach equilibrium, as we said. So suppose it would perhaps move a certain distance dA, and if it was solid, then it would reach equilibrium there. So the line AB would be rotated by an angle delta beta and move to the line AB prime. Now, a shearing stress would develop there. Let's call the shearing stress tau. We usually use the Greek letter tau. And that's going to be equal to the load applied P divided by an area of the plate. Of course, these plates are infinite, but this is an idealized situation. And equilibrium dictates that these are going to be equal. This is the situation for a solid. It reaches equilibrium. Now, if the material is fluid, then the upper plate is going to move continuously with a certain velocity. We no longer have this equilibrium that is expressed in this equation here. We have a different situation. So the shearing stress now is something different. So we have, again, I have the same figure that we had before. The upper plate moves due to a load P. The distance between the two plates is B. And we have this point A, B, which has rotated to the line A, B prime by a angle delta beta. Okay? So if the material is a fluid, then the fluid deforms continuously. And therefore the upper plate moves continuously with a certain velocity. Let's call it capital U. And so we have a certain velocity here, capital U, for the upper plate. And let's call these Y and X our axis. And in this situation, because the material between the two plates is a fluid, it will move continuously. The upper plate moves at a velocity U. What happens in between? To know what happens in between, we consider this experimental fact, which is called the no-slip condition. The no-slip condition is the experimental observation that a fluid moves with the solid boundaries. So the top layer of fluid, which is right next to the top plate, is going to move with velocity U, capital U, and the layer of fluid which is right next to the bottom plate is not going to have any velocity. It's just static there. In between the top and the bottom plate, we will have a velocity, the fluid between the two plates moves with a velocity which is a function of my vertical coordinate y, u is equal to u of y, and in this case this is a linear relationship, a velocity which varies linearly as u, small u, is equal to capital U times y divided by b, the distance between the two plates. So what we have is that there is a velocity gradient here, the velocity gradient of u with respect to y. There's a velocity gradient du dy, because the distribution of velocity is a linear distribution, then the velocity gradient is a constant, and this constant is equal to capital U divided by v, capital U being the velocity of the top plate. That's our velocity gradient. Okay, so now we're going to consider a small increment of time, delta t. The line AB, as we said, rotates to the line AB prime. So AB rotates to AB prime. And notice we're saying it's a small time increment. In the sketch, of course, it looks like a very large angle, but we are mathematically considering a very small time increment, and so a very small angle. So the picture here is exaggerated, but it's a small angle. Delta beta. And we can make the small angle approximation, which is that the tangent of delta beta is approximately equal to delta beta. Small angle approximation, okay? And also we see that, again, the distance between the two plates is b. So this is going to be equal to the distance traveled by the top plate delta A divided by B. Now this is moving constantly, so we're considering a small time increment, and during this small time increment, the plate moves delta A, and so we can write that delta A is equal to U times delta T, and therefore we have that delta beta is equal to delta A divided by B, so U delta T divided by B. Now, so the angle delta B varies with time, right? But we're looking at a very small time increment. And the angle delta B varies with time at a rate which is defined, which is this rate is capital U divided by B. So the angle delta B changes with time, and the rate is called, at a rate called the rate of shearing strain. This is what we call it, the rate of shearing strain, and we use gamma dot to represent the rate of shearing strain, and it's going to be defined as gamma equals to the limit when delta T tends to 0 of delta B divided by delta T. In this case, if we divide delta T, we just get U over B. And we're going to finish here. We find here then that the rate of deformation, we find then that gamma dot is equal to capital U over B. From this expression here, we divide by delta T and we take the limit, nothing happens because it's a constant in this case, U over B, which is equal, from the previous slide, to du dy, which is the gradient of the velocity. Now, in general, the velocity gradient is not going to be a constant. It is a constant in this very idealized situation. But it is true that the velocity gradient is equal to the rate of shearing strain. Now, the rate of shearing stress can be related to the rate of shearing strain, and we have found experimental, not we, but all the some fluid dynamicists, experimentally, it has been found that the rate of shearing stress tau can be related to the rate of shearing strain, and it has been found that they are proportional to each other. This is an experimentally observed fact. And the constant of proportionality is what we call the viscosity. So I wrote that I've run out of space, so I'm going to write this again. We have experimentally that tau is proportional to gamma dot, so the rate of shearing stress is proportional to the rate of shearing strain, and the constant of proportionality and we'll use the Greek letter mu, is the viscosity. So tau is equal to mu times du dy.